As you can see, the person, the first at the front, Yassin Zagar, who did the research, it's part of his master's thesis, and Arnoud Visser was his supervisor, and he was very interested and keen on the fact that this work was appreciated, so that this article was published, and due to circumstances, I had to do the presentation. Arnoud wanted to do it, but for reasons he's not here. The major thing done by Yassin is that he combined three algorithms and made a concatenation of them, a sort of pipeline, and tried to show that this is more robust than each of them separately. And the reason is something else, is that going towards smaller and smaller flying machines, there is no reason to think of a sort of Christmas tree flying around with numerous sensors. The weight or cost and energy will be too high, and your performance in flight time will reduce to several seconds or minutes even. And the idea is that if you have a machine like this equipped with a camera, a single camera is about the limit. Maybe in the future, if we have more energy aboard in more advanced batteries, maybe we can go to more sensors. But for now, we limit ourselves to monocular vision. And based on that, we need more algorithmic power to finally do avoiding obstacles in a common environment. And common environment is more or less what we can think of trees in a forest. And not something specific as an environment. It could be trees in a leaf-covered surroundings, or rocks, or grass. And finally, the idea is that if the algorithm is strong enough, that it's not only something like trees and stems of trees, but also other objects are possible to avoid. And again, the basic line is showing the robustness of the chain of algorithms. And that's also the background of the testing that I will show later on. So, in 2D final image, it's difficult to find depth, and for that to find the obstacles you want to avoid. So, the idea is to solve this problem, and the speed we're trying to solve this for is 1.5 meters a second. It's a little bit arbitrary, but it's a speed that can be maintained now, and that sense is for that speed we have a real-time operating system that can do the algorithm in such a time that obstacle avoidance is to a certain degree guaranteed. By the way, the kind of quadcopter we use is the type as shown in this image. It's just available as an object, and that is what is the starting point of the hardware. So the difficulties we are facing is that not only the types of obstacles, that they are thin or big, is the texture, the shape, are they rigid or do they deform in time? What are the locations compared to other objects? So there's a chain of problems that should be tackled if your algorithm is robust enough. For the time being, we have static objects, and the major differences between the two test environments is that the first test environment is thin, vertical, tree stems in that sense is a nice representation for that, and to have a more idea about the robustness of the total algorithm is going to objects that are bigger, and the big difference is shown already in this image, is that the left image, the objects do not cover completely the image. Like in the right image, the object in these two cars is that the left car is not completely in the image. If it is in the image, it would completely cover the image. So there are no conclusive connected to what is the object. It's too big to do something. So this is an arrangement that should show the limits of the algorithm, because you have to find the background and the foreground. So the only thing between that and the two images is that the car is man-made, so you could have information in the background that tells you what kind of object it is, so it makes the matching maybe simpler. For the trees, there's no use to have some sort of global definition, because they could be different in many ways. The only thing you can talk about that you saw some sort of appreciation of a certain size and a certain distance. However, you don't have to stick to a certain kind of tree, because it is known that the same shape of tree can have different sizes because of age or the type of the tree. But for a first estimation, you can say if the tree is a certain size, it's nearby; if it's smaller, it's further away. To really work with this kind of distance measures, you maybe need additional sensors like rangefinders, stereo cameras, distance sensors, etc., etc. But the start of the talk was that you want to have less sensors concerning the size of your machinery, the lift possibilities of the machinery, and of course the energy consumption. So you want to stick to a single monocular camera. One of the starting points is looking at related work, and it was optical flow that brings in mind that optical flow can give you the information you need concerning what is nearby and what is far away. Because if you move with your object, you can notice that in this case the right image is that the highest level of light, the white dots, is the location with the highest optical flow. So the conclusion, that's most nearby spots, and that's the location you need to get away from. So that's first indicators that you need to stop and to decide on a different route to fly. So the proposed method is a complete pipeline, and if I'm correct, this is the pointer. Now find the front side. Yes. This is the whole pipeline. I will go into detail in this part and in this part. And the top part is first try to find a sort of manner to subtract the background, because far away background is accepted as not interesting. It's the foreground that contains the objects you want to miss. And if the background is gone, and there has an extra reason, is the number of data points you are going to calculate is less. Because the background is normally disturbing, has a lot of data that's not useful, you want to get rid of that. And if that is manageable, you have a foreground, then the foreground is the data set you want to do optical flow tracking. So it's getting rid of the background, then you filtering, and finally, then is your data set in shape to do optical flow tracking. And that means indeed a reduction in data, and it can finally do this part of the algorithm in a real-time manner with the speed of 1.5 meters a second. Finally, if this stage is done, then it's possible to finally get enough information, enough to control the flight control, so that the quadcopter is able to fly its trajectory as needed. So first, background subtraction. We're not jumping to the trees right away, but give some background information that indeed contains a lot of data that you want to have. Like for instance, this background gives a lot of data. And the algorithm is able to find disconnected, for instance, this is foreground, and there are a lot of connected pixels and a lot of disconnected pixels sitting here, so it's easy to find them and get rid of them. And finally, you get this more smooth image, and this is an enormous reduction in data, and that's the moment that you want to, that's the kind of data you want to feed to the optical flow unit. So the optical flow unit is focusing on what is seen already as the foreground, but you don't have any depth. So you don't know what is in foreground as a first object or second or third object. So that is the next stage to find out. So what you need is sort of form of feature detection. So now there is really a first object in front, and you want to see what's going on there. Now, you want to isolate the features, and the effect is that the processing load is lower, the increased false positive are there, and that will affect the drone controller. So you want to get rid of those funny, disturbing loose pixels sitting here. So you want to do again reduction of. And finally, by clustering and find the condensed point, this survives. And it gives you really a good feeling about that this is the road to go, and find the clusters that can be appreciated as the clusters representing something in front of the background. So finally, the last stage of the of the box shown here is, by the way, is this readable in the? It says depth fragmentation and proximity. These two are needed, the proximity estimation. And together, it gives you all the data you need to have the right input to your flight controller. Because depth segmentation is one stage you need to estimate your proximity near to the objects you want to pass by. So depth classification, that's other work done by people, and it gives nice information, and you can see maybe they're too small, but the front side, and this is a rotating object, the front side, of course, is moving faster relatively compared to that part. Radial movement, so the vectors are longer than in this area, and based on that optical flow vectors, you can estimate the distance and the distance to your flying object. So the classification in that stage should be fine. The experimental setting is a parrot air drone, the 2.1 version. And the environment is lighting everywhere, so it's not a single lighting point. There are reflections, there is clouds, there are shadows. So it's really abundant illumination. In this case, very low wind speed. To have surroundings like this and to rebuild it inside to reduce the wind speed is a little bit ridiculous, so you go to the outside, but still you don't want to have your quadcopter blown away by funny winds. So, okay, wait for the right day. And the first test was done with a single narrow obstacle, and then hopefully it was possible for this algorithm to also pass by 2 narrow obstacles. And as a final test, 2 wide obstacles who are more filling than the size of the image. Other things is what we did, and I have to go back to this part, is to switch off certain parts within the total pipeline. Why? Is to more or less prove that the whole chain is needed for business. If you switch off parts, it will be shown that the algorithm is not robust as we think it should be. So, okay, the first single obstacle, and the colored lines give the kind of trajectory the quadcopter has flown, and this is with the full pipeline active. And depending on a slight difference in the starting point of the quadcopter and the flight conditions during the flight, the quadcopter can decide to go passing left side of the tree or right side. And in the 5 tests, 4 times it was tuned to go to the left side and 1 time to the right side. The reason for this kind of small hiccups in the flight that could be by shadows or other small disturbances in the environment. So this is the situation. And what will happen if you don't do background subtraction? just to get a feeling if this is really a necessity to do this. And if you do this, you switch off the background subtraction. You get a lot of locations that also will be incorporated in your calculation of the optical flow, and the result will be this. It's clear that the algorithm will be less robust as in the total pipeline. Some will pass, they will go fine, the green and the purple line prove that, but there are situations that the machines are not reacting in time because the data set is huge, and the other thing is that it doesn't recognize the tree at all because it's blurred by the background hits and effectiveness. So the flight is successful, but partially. So now done with our proximity estimation. So the background is switched on again in the detection, and the proximity is switched off. And this gives a nice result in the fact that it behaves quite roughly. It just notices something in the front and does one big guess, and it goes to the left side always. And that's not a real nice solution, because if you switch to a second object in the background, it could be path blocking, because the right situation is not available anymore. It sticks to a certain appreciation of the situation and finalizes in an unblocked situation. So now without the depth classification, and we get the following situation. And that seems quite good. It's only 5 tests shown here. There were about 1,000 tests done in test runs and in simulation. But small disturbances are effectively leading to a collision situation. So you're not really happy with this kind of classifications. With depth, you're losing interesting information. So going to 2 narrow obstacles, then in that case you really need all the information. So the first image, that's the one to the left. The whole pipeline is active, all algorithms are switched on, and we have a sort of 100% fail-safe trajectories over all tests. If we switch off the estimation, the depth estimation, then we get the situation like with the first single tree in front. One track is chosen, and that's about it. So if there is a third tree in the background, it could be blocked again. And without classification at all, it does something, but bumps into the second tree because it sees the second tree as part of the background again. So the first tree is seen as foreground, and the second tree is seen for partly in some situations as background. So this gives more or less the idea that the complete set of 3 algorithms are really needed. Now in the 2 wide obstacles, and see what my time is giving me. Got some 3 minutes left. Targeting what is foreground and background is maybe not the biggest problem, but seeing a difference in what is foreground, because if the object is too big, then it's the complete foreground is the complete image. And that means that for the object to fly in a purposeful way, is that it doesn't see anything than a solution that, okay, to the right is the best solution, that's about it. There is no idea. Or it switches to the left side. The objects are just too big and too image filling. But still, if you have the proposed method with all the pipeline in working, only one of the, I think it's 1 out of 10 or 20 will bump into the car. That's the green line. It shows that it bumps in car 1. And in this case, it more or less shows that without estimation, you have better performance. Just go to the left. But the flight time increases because it starts jittering. It is going up and down here. It tries to find a way around. And why it doesn't go in that direction? Because it thinks that this is completely one background. So the only thing is to go around. And the decision should be taken in flight time, because it was not in the starting image. So it should build up some information during the flight, and then finally it sees an escape and goes to the background. And finally, without classification, it goes terribly wrong. It just flies into the first because there is no idea what is background, foreground. It just sees one object and it sees everything as background. So for the object is free path going to infinity. So it bumps into the first car already. So this more or less gives the idea that the full pipeline is needed, and even there is needed more. If you stick to monocular vision without other sensors, we've shown that the first 3 stages are there. It gives a more or less robust situation, but for several cases you need more. So optical flow could be used for obstacle avoidance, but the depth proximity methods significantly help improve results. That is clear. By switching off we can prove that. The background situation, subtraction plays an important role in getting the right focus and also getting the right performance concerning the amount of data you have to process. So the final question, the conclusion is we have a flexible framework. It's extendable because the pipeline could be improved. And it shows also the combination of methods that you can have a better model of the situation you want to feed to your control system. And in this case, with 1.5 kilometers per second, we are capable of running in real time without prior training. So no training, just an image, and the control will be done. Thank you. Are there any questions?
Test your system for narrow obstacle, for very narrow obstacle.
The question is, did we test our system with really narrow obstacles? I think you refer to really narrow compared to a tree-size object. Probably they did, but I don't know any test results of that, so I presume real narrow objects wasn't delivering anything nice. I think that's the answer of the situation. Yes, thank you.
Can you turn back to the graphics that you have shown about the top views? So how did you get the data for the paths? This shows the top view image of the scene.
Yes, good question. I have to refer to Arnoud Visser to answer that one. Yes, because there are several ways. I don't know which one is used for this specific image. Yes.
Can you say something about the capabilities of handling moving, especially rotating objects?
Oh yes, that's clear because there is no learning involved. It's just the image as it is, and because the quadcopter is moving during the excision, there is no difference in that the objects can move. It's a relative displacement of the position. So the objects may move.
Okay. But I was actually aiming for especially rotating around a vertical axis. So if you would go back to the Rubik's Cube and you would have it rotate around the vertical axis, wouldn't that mess up your proximity estimation due to optical flow?
The question is that if objects are moving, in the specific sense the objects are rotating, they could appear more in front, of course, yes. I think you got something that is really disturbing for this kind of algorithm. Yes, indeed. Yes, because in that rotating will give you optical flow effects that's now interpreted as nearby. Yes. Okay, so extension of the pipeline already here proposed. Thank you. I need to watch the time. I think one final question is, yes?
Is there any specific reasons the trees were painted in white in the bottom?
Yes. There was no specific reason for that. It was like that during flight.
Okay.
Yes.
So it was not done to increase the visibility?
No, the painting of the trees was something that was in the image, and didn't do anything. It's just the structure of the tree is most interesting. It's the form of the tree. We don't do anything with color or whatever. That's the idea. Thank you. I don't know who is the